In this lecture, we want to cover a combined isotropic and kinematic hardening. So we've already talked a little bit about both of those separately. Now I want to combine them, and I'm going to talk a little bit about the formalisms associated with coming up with the scalar hardening function in these conditions. And since we haven't talked about the scalar hardening function for kinematic hardening, we're going to go ahead and specialize the general case to that as well here. So let me just refresh your memory here. So let's say recall that if we had, let's say, for a von Mises yield function, okay, so for a von Mises yield function, we had, in the case of isotropic hardening, so in the case of isotropic hardening, we wrote that F was equal to J2 minus J2 bar, which we said could also be written as J2 minus 1/3 sigma bar squared, where sigma bar is the uniaxial yield stress. Okay? Something like that. And we've also talked about kinematic hardening. So let's just refresh our memory on that. So kinematic hardening. And we developed a yield function for this. It looked like F, instead of writing J2 in this form, we actually wrote it out. Remember, J2 is just 1/2 Sij, where S is the deviatoric stress tensor. So the kinematic case shifts that. So it's Sij minus alpha ij, where alpha was the back stress tensor, you'll remember. Sij minus alpha ij. So that's the equivalent of J2 as we're shifting it. And then we could just say minus 1/3 sigma naught squared now, right? So this quantity remains constant. It doesn't change. Okay? So in both cases, we had internal state variables. So internal state variable. Okay, and then in the kinematic hardening case, our back stress was a set of internal state variables, right? Okay. Okay, so now we're going to introduce a couple assumptions, okay? So here are some assumptions that we're going to use going forward. So number one, we're going to follow the Melan-Prager expression for back stress. So, okay, I'm going to follow the Melan-Prager expression for back stress. Okay? And when we do that, that says that the increment of the back stress, d alpha ij, is just directly proportional to the increment of the plastic strain. So it's, let's say, C times d epsilon ij plastic. Or you could write it in rate form if you want and say that alpha ij dot is equal to C times epsilon ij plastic, the plastic strain rate, right? Let's call that equation 1. Okay, the second assumption that we're going to make, in what we did in the case of isotropic hardening was we just said we just want to expand this yield surface. It's going to be more convenient as we develop this more general expression to relate the hardening, the isotropic hardening component to the plastic work. Okay, so we're going to relate the isotropic hardening component of a general hardening law. So isotropic hardening component, right? So that would be kind of effectively replacing the sigma bar here, but we're going to relate the isotropic hardening component to the plastic work. Okay? And we could write the plastic work as the integral of Sij times d epsilon ij plastic, right? That basically gives us how much this is all dissipated, and we could also infer from this that d the increment of the plastic work is just equal to Sij times d epsilon ij p. Okay? Let's call that equation 2. Okay. Now I want to remind you that we already had a flow rule, and that flow rule remains unchanged. So the flow rule is the same, and let me remind you what that is. Okay, that during yielding, we can write that the plastic strain increment, d epsilon ij plastic, is going to be equal to the scalar hardening function g times the partial f with respect to skl, dskl, right, times the partial of f with respect to Sij, right? That was our flow rule. Remember, we require that f was equal to 0 and the partial of f with respect to Sij, dsij be greater than 0, right? That was required. Okay. So now what we want to do is, okay, so having reminded you of the flow rule and now taking these assumptions, I'm going to use these assumptions to propose a new flow rule functional form. So use these assumptions to propose a yield function of the following form. Yield function of, let's just say that f, I'm not going to write out the equation explicitly here. I'm going to say it's a function of, we know it's a function of Sij. We know that it's also a function of epsilon ij plastic, right? How do I know that? This is through the Melan-Prager rule that I just showed you up here in equation 1, right? The back stress is going to be related to that. And then the isotropic component is going to be related to this plastic work term, okay? So this quantity here, right, epsilon ij plastic and the plastic work, those for this case are our internal state variables, right? Which we originally, when we were talking about this generically, we called that Q, okay? So that's the form that we have. So now what are we going to do? Well, let's think about what the consistency condition gives us. Okay, so let's consider the consistency condition. You're probably going, I have no idea what that was. I vaguely remember hearing about it multiple lectures ago. I'll remind you. Okay, if I can spell consistency, condition. Okay, what is the consistency condition? It's that during plastic flow, right, F must remain equal to 0 so that dF must be 0 during yielding. That's the consistency condition. Okay, so what does that give us? Well, let's do our chain rule. dF then is equal to the partial of F with respect to SKL, dSKL, plus the partial of F with respect to epsilon ij plastic d epsilon. I should keep consistent on my indices. KL, KL. This is plastic, plus the partial of F with respect to the plastic work times the increment of the plastic work. Okay, and of course that whole thing has to equal 0. Okay, I can go ahead and do a little rearranging of that and write that this quantity, the partial of F with respect to SKL dSKL, which we know is contained in our flow rule, that's going to be equal to negative of the quantity partial of F with respect to epsilon KL plastic d epsilon KL plastic plus the partial of F with respect to the plastic work times the plastic work increment. Let's call that equation 4. So what I'm going to do is I'm going to substitute 4 and actually 2 into 3. Okay? So I'm going to go ahead and substitute 2 and 4 into 3. Right? 3 was just my original equation for the plastic strain increment. So d epsilon ij plastic was equal to g, and it was g times the partial of f with respect to skl times dskl. I'm now going to substitute this thing in. So I'm going to have a negative sign there. And then I have this quantity, partial of f with respect to epsilon kl plastic, d epsilon kl plastic, plus the partial of f with respect to the plastic work times the increment of the plastic work. And then, of course, I have this partial f with respect to Sij as well that I have to be concerned about. Okay? So what I'm going to do is use this quantity. This we said was Sij times d epsilon ij. I can see that I can't use ij, so I had better use different indices. Right? So how about I use KL? So SKL d epsilon plastic KL. Okay? And now what you can see, I hope, is that I can pull out a d epsilon KL and a d epsilon KL. I can pull that to the outside. So I'm going to go ahead and do that. So that I can write d epsilon ij plastic is equal to negative g times the quantity, the partial of f with respect to epsilon KL, plus the partial of f with respect to plastic work times SKL, that quantity times partial of f with respect to Sij, times d epsilon KL plastic. Okay? Let's call that equation 5. So what I have here, let's think about this whole quantity right here. Okay? What I have is that the plastic strain increment is equal to something times this plastic strain increment, but my indices don't match. I have an ij here and a kl here. The only way this can actually be true is if this quantity I just underlined is delta ik, right, that swaps the indices, times delta jl. Okay? So let's go ahead and write that equation out. Okay, so what I'm going to end up saying is that negative g times the quantity, partial of f with respect to epsilon kl. I'm going to bring this partial f with respect to Sij inside, plus the partial of f with respect to the plastic work times skl times the partial of f with respect to Sij. That quantity we said must be equal to delta ik delta jl, right, in order for equation 5 to be true. Okay? So how do we solve now for this? We're trying to solve for the scalar hardening function since that's what we don't know. So how about we multiply by this quantity on the right? So multiplying by delta ik delta jl, we end up with negative g times delta ik delta jl times, I'm just going to write this now as that, right, what I had. I'm going to write it all out right now. Now I have delta ik, delta jl, delta jl. This is actually a homework problem. This quantity gives us 3. This quantity gives us 3. So we have this equal 9. Okay? Now let's go ahead and think through this other side. I still have my negative g here. But now as I look inside, I'm going to change my k to, either change my k to an I or my I to a k. I'm going to go ahead and change my I to a k, but it's equivalent. It doesn't matter. So I can write this as the partial of f with respect to epsilon kl times the partial of f. Now I'm going to swap the I, make the I and the j a k and an l, so it's partial of skl plus partial of f with respect to WP times SKL. Do the same thing here, partial of f with respect to SKL. Okay, that's going to be equal to 9. Okay, and what I can do is I can go ahead and solve for G now. So that G is equal to negative 9 divided by the partial of f with respect to epsilon KL times the partial of f with respect to SKL plus partial of f with respect to plastic work times the partial of f with respect to SKL times SKL. Okay, so there's our scalar hardening function for the general case. And you're probably going, well, that seems unhelpful. Hopefully not. Let's see what that tells us. Okay, what does this really tell us? Well, let's think. The important feature here is that if I know F, I know G, right? So what we can say is that G is completely defined by F. Okay? By F. Okay, that's an important result. It means that it's not a mystery. We can compute that directly. How about in the case of kinematic hardening? Well, in the case of kinematic hardening, that's just a specialization, right? So in the case of kinematic hardening, what can we say? There's no plastic work component, right? So in the case of kinematic hardening, the partial of f with respect to plastic work will be equal to 0. Okay? So that means that equation 7 becomes G, and I'll put KIN for kinematic, it's going to be equal to negative 9 divided by just the partial of f with respect to epsilon KL plastic, and I should put plastic here, times the partial of f with respect to SKL, right? That's, call that equation 8. So again, if we could write that down, that would be a straightforward thing to do. If we could write down F. And I'll also say that we have to come up with something. There's no one way to define the yield function in combined isotropic and kinematic hardening, but I'll just give you one possible example. So I'll say that for a possible, make sure this, you can use it, but it's not the only thing that you could use. So for a possible kinematic, isotropic, combined hardening yield function, hardening. Okay, if we wanted that. So this is for a possible combined case. We might try something that looks like this. Right? Something that says F being equal to, now let's just take the kinematic side, which is 1/2 Sij, now minus C times epsilon ij plastic times the same quantity, minus C times epsilon ij plastic, right? Minus 1/3, and instead of sigma naught squared, it'll be sigma naught. But then we also want to say, well, it's going to grow somehow. So it's G, let's say, times the plastic work, right? And in this case, C, that value that describes how the backstress moves, and G, the quantity that describes how fast the yield surface grows, those are constants, right? That would be an example of a very simple combined kinematic isotropic hardening model. Of course, once I've written this, I can call this equation 9. Now that I've written this equation 9, it's pretty easy to go back into equation 7 and compute all those derivatives and compute G from that. Okay, so it's fairly straightforward. And then obviously I would compute the constants from, let's say a uniaxial tension case, but to calibrate I'd have to know not just a single load up, I'd have to be able to unload and see how that yield curve shifted. So I would need more than just a loading curve, right? So anyway, that's sort of the more advanced case of what we've been trying to do. Hopefully it's straightforward and dovetails with all the things that we've talked about so far.